Okay, so this is part 2 to the exam review. So this will cover section 10.1 and 10.2. Again, I'm not going to work out any examples in this one. I've worked out plenty. I did do an example in 7.8 just because there was something we hadn't seen before, so I wanted to show you that not all integrals with discontinuities in the middle diverge. Okay, so let's talk about curves defined by parametric equations. So, we're used to seeing, equations of the form f of x, y is equal to 0, or, y is equal to f of x, or x is equal to g of y, things like that. Parametric equations are different. So parametric equations are of the form. So we will still have, x and y, except now instead of being dependent on each other, they're going to be dependent on functions of t. And so the idea is, being able to write this down lets you do, a brand new class of problems where you couldn't write down, a function for some of these curves. So these are given to you, any problem, these will be handed to you. And so what you can do, so you can, graph these if you need to. You'll make a chart where you plug in values of t. So, you do equal t equals -2, -1, 0, 1, 2. And then you would figure out what x and y are by doing f of -2, g of -2, f of -1, g of -1, etc. And then you could, you plot the xy points and you get, whatever curve, is being described by these things. So, that's how you plot them, but there are a couple important curves. Circles are important. So the first one we saw is x is equal to r cosine of t. Well, so let's do x is equal to cosine of t, y is equal to sine of t. This is a circle of radius 1, parameterized counterclockwise. What I mean by parameterized counterclockwise is, if you were to, start plugging in values of t and getting x and y points, what this would do is it would start here, and as it drew out, it would draw out in this direction. It would be more circular than what I'm drawing, but, so, the idea is, these curves have a direction, and this one is counterclockwise, and I've drawn it correctly this time. So you can, change the radius by multiplying by, whatever r is. So y is equal to r cosine theta, y is equal to r sine theta. This would be a circle parameterized counterclockwise, radius r. You can do some more manipulations that I covered. So you also have counterclockwise circle. And for those, you can do two things. So you could either do x is equal to sine of t, y is equal to cosine of t. So you just switch the sine and the cosine. And what this is going to look like then is, so at 0, you start at y equals 1, or you start at the point 0, 1 there. And so, as t increases, instead of going counterclockwise, you now go clockwise. This will give you a circle parameterized clockwise. There's another way. Sorry, this is supposed to be clockwise. So there's another way of parameterizing this. You could also do x is equal to cosine negative t, y is equal to sine of negative t. And again, this will, reverse the, it'll change the parameterization. Because cosine is even, this is just cos of t. Because sine is odd, this is minus sine of t. So this will give you another clockwise parameterization. There are some shifts you can do. And that's going to cover that. So, we talked about graphing, circles are important. And then we moved on to section 10.2, which was calculus. So what that's gonna be is, if you have a parameter. So for these, for these, I'm gonna have parameterizations. X is equal to f of t, y is equal to g of t. And then, so, the question is, how do I compute dy dx? I do chain rule. So what this is going to be, is going to be dy dx is equal to dy dt divided by dx dt. You also have the second derivative, d squared y dx squared. This is going to be, instead of just turning those both into second derivatives, that's not what it is. You have to do this. It's going to be d by dt of dy dx over dx dt. The idea is, you'll take this and plug it in to there. So that's a little more complicated, but it's doable. So you have to, just remember that it's not just taking this first and second, or the second derivative of both of those things. We also talked about integrals, so areas. So the way you do that is, if your parameter starts at t is equal to alpha and ends at t is equal to beta, then the integral from, so if you had, the original integral, a to b y dx, remember here we're going to assume x is equal to f of t, y is equal to g of t. This is going to become the integral from alpha to beta of y. So y is g of t. And because, x is f of t, its differential is going to be df dt times dt. And so, given these functions, you can determine, this area. And I think the last thing we did was arc length. So the last thing we did was arc length for this one with parameterization. So again, we're assuming we have x is equal to f of t, y is equal to g of t. Again, our parameter starts at alpha, ends at beta. Then the arc length is going to be defined as the integral from alpha to beta, square root of, and now the form of this changes. It's going to be dx dt squared plus dy dt all squared times dt. So that's different than, our formula that we had originally, but it still holds for. But this is how you do it for, parameterized curves. So that's going to be, again, I'm just covering the high points of each section. This is not, comprehensive review. There are some things I'm leaving for you guys to look up because they are in my old videos and they're also in the book. So again, if you have any questions before tomorrow, feel free to email me. I'll try and respond to them. But yeah, so that'll be it for the review.